be happy.
Okay.
Yeah?
Try it. Yeah.
I'm going to click it. We've gone live. Okay.
And let me see. Alright. Thank you. Let me just...
Sound check.
It's not up. I'm just going to reload this. Yep. Okay.
Okay, we're just going to do a few little checks before we begin. So, sound check.
Yep, it works.
Awesome. Okay.
Yep.
So, the time right now is 4:01. And we're going to start at 4:05, just 5-minute wait period. And before then, we're just going to ask everyone to register attendance, just so that we can get our numbers right for this presentation. Yeah?
Nice. So, yeah, we'll just chill for the next 3 minutes.
Okay. So, this is the Math1231 or 1241 revision seminar for algebra. Term 2 2023.
Yes. Please check out yesterday's one for the part 1 if you wanted to look at the calculus. That was done by Marcus and Jess. It was lit, so yeah, go check that out as well.
Yeah. Alright, we'll start in just a minute. And before we start, a little bit of an introduction. I'm Otto. I've got my friend Aaron here.
Hi, yes, I'm chilling on the side, yeah.
We're covering algebra today. I'll be covering vector spaces, linear transformations, and eigenvalues. And I'll swap over to Aaron when we get to probability. And that should be from 4 till 6. We'll be happy. Okay? Alright. I'm going to start now. So, here's our overview, and now we're going to move into vector spaces. So, first important thing we'll get to in vector spaces is our subspaces, okay? And essentially what a subspace is just a vector space inside a vector space, yeah? Some subset of a vector space, if it follows the conditions of a vector space, it is a subspace, yeah? All right. From this, we have our subspace theorem, which gives us 3 essential conditions for a subspace. So, the subspace must contain the 0 vector of the vector space, and it must achieve closure under vector addition and scalar multiplication, okay? So, fancy word closure, essentially all we're saying is following these definitions here, if we have 2 elements of the subset, and we add them together, we're going to get another element from the same subset. Similarly with scalar multiplication, if we take the scalar multiple of any element in the subset, we're going to get, once again, another element of the subset. So that'll make a subspace, okay? So diving straight in, we've got our first question here. So for subspaces, I have like 3 main points to make, okay? And those are just going to be quick things that we can look for, okay? So the 3 main things I look for when I am faced with these kinds of subspace questions are our operation, whether we have a 0, and if we have any indices, okay? Any exponents to our values, okay? So in this example, we have a greater than or equal to sign, okay? So, because we have a greater than or equal to sign, just immediately, I can show that, okay, S is not a subspace, because if I use a scalar multiplication, letting lambda equal -1, I can immediately say that, okay, if x1 plus 2x3 is like 6, okay? As soon as I multiply everything by -1, so I make x1 minus x1, and I make x3 minus x3, we will have to flip the sign. And that no longer holds for this condition, Okay? All right. So, more formally, we're just going to go through our three essential components to prove a subspace. Okay, we're going to apply subspace theorem. First thing, is 0 contained in this subspace, in this subset? Okay, so 0 is our 0 vector, so x1, x2, and x3 are all going to be 0. So this is 0 for R3. We can show that this is definitely in the subspace, because once we substitute it, it satisfies the condition. Done. Next, we got to prove closure under addition, okay? Closure under vector addition. What we're going to do here is we're going to take two arbitrary values of the subspace, okay, with their conditions being just already true because they're in the subspace, and we're going to see if our addition of them is true because of this very same condition. Okay, so if we let u and v be two different elements of S, we can clearly see that very linearly we can partition their sum into the two given equations, okay, the two given conditions, since those two vectors, u and v, are already elements of S. So we get that the sum is in S, our subspace, our subset, rather. So, next, the last thing we got to do is to prove the closure of S under scalar multiplication, okay? So one way we can do this, a very rigorous way, is to say, okay, if we have some vector u, okay, and then we multiply it by lambda, a scalar, does this hold arbitrarily, okay? So if we get into it right here, what we've done is we've attached some lambda to it, and we can say, okay, three main tests for lambda are 0, -1, and some positive number, okay? And does it work for those three? We can see right here that for the scalar multiple, -1, it does not work, okay? Because substituting -1, we get -1 plus 2 lots of -1 is -3, which is, in fact, less than 0, rather than greater than or equal to. And that's done. That's the question done. We've proven that it is not a subspace, okay? The reason being it is not closed under scalar multiplication. Okay, next question. We have, suppose that the set S in R3 given by x1 squared minus x2 squared equals x3 squared, prove that this set S is closed under scalar multiplication. Now, just as a little additional note, I'm going to get us to also consider whether this satisfies the subspace theorem, okay? Is it a subspace as well, okay? And the reason being is that this question has exponents. It has exponents in the condition. All right, so first part of the question, prove that it is closed under scalar multiplication. So, as we said before, we're going to attach lambda, a random scalar, to our any vector u, okay? Any vector that is in S. So, once we do this, we say v is x, y, z, where v is an element of S. So since v is an element of S, v is any element of S, we know that this condition holds, okay? So given the value of v, okay, it being an S, we know that the condition is true. X squared minus y squared equals z squared. When we consider lambda v, which is just any scalar multiple of v, and we plug it back into this same equation, we can see that the lambda distributes to all of the components. And from that, we can just, well, rather it distributes evenly to all of them, yeah? So each expression in this condition has lambda of the same multiplicity, lambda of the same exponent, index, yeah? So since it does, we can say that, oh, we can just divide by lambda, and we're done, yeah? We may need to account for the special case of, okay, what if lambda was 0? Because we know that we can't divide by 0. Well, if lambda was 0, that's just going ahead and saying, okay, is 0 an element of this, okay? And we can clearly see that substituting 0, we get 0. the condition is satisfied, 0 is in it as well, so we've accounted for all lambda. Okay, so for any scalar multiple, for any v which is an element of S, we have closure under scalar multiplication. Okay, and we're very happy right there. So we're going to just bring it back a little bit. The little additional question here was, but is it a subspace? Okay, we've seen that we have 3 conditions, which is 0, addition, and scalar multiplication, and we've ticked 2 of the boxes, yeah? Essentially, if there's scalar multiplication, we know there must be 0, because what if lambda is 0? If lambda is 0, we're just accounting for the 0 vector, okay? So, to check if it is a subspace, we have to check the vector addition condition. So, if we have u and v, which are elements of S, is their sum still in S? Okay, so as I said before, one of the important things to look out for are the exponents, yeah, our indices. So we can see every term is squared here. So if we have v equals x1, x2, x3, and we have y equals, actually, rather than y, I'm going to try distinguish v from u here. So we'll have u equals y1, y2, y3. So this gives us 2 things which are true, where if we substitute x for y, we have u's condition, and x as it is, we have v's condition for being in S. Now, we need to consider whether v plus u is in the set. So what this implies is, okay, is x1 plus y1 all squared minus x2 minus y2 all squared, is that going to be equal to x3 plus y3 all squared? Very clearly from this, we can see that, okay, when we break down all of these squares, our x1 plus y1 becomes x1 squared plus y2 squared plus 2 lots of x1, y1. Okay, we can cross out our x1 squared and y1 squared in each of the terms, because those are just our conditions for those u and v vectors being in this subset. What we're left with after all of this is, okay, is 2 lots of x1, y1 minus 2 lots of x2, y2 equal to 2 lots of x3, y3. And the result of this, we don't know, okay? We don't know. There's nothing given about the specific values of x1, y1, x2, y2, and x3, y3, okay? So we cannot conclude that it is closed under vector addition. Another thing we can do is, okay, to prove, okay, that it is not closed, we can then formulate an example where this equation that we just had, derived from u plus v, the addition, we can substitute 2 random values within S to see if it satisfies this very condition. Yeah? So there we have it. We've done the question. We're very happy. So I'm going to take a little moment to pause and just read the comment section, see if there's anything that we need to double check. Okay? Any questions, feel free to throw them in there. Okay. Spans. Okay, spans are going to come next. Span. Okay, what is a span? A span is essentially when we have a set of vectors. A span is how can we stretch them, how can we put them together, what linear combinations can we make? Yeah? So, a linear combination is essentially how many, if you consider every vector, okay, as just a little piece of Lego, different shapes, different sizes, right? The linear combination is, okay, if you have infinite many of those different types of Legos, what are all the different things you can make with them? Yeah? As a really, like, fancy way of putting it. So, anything of the form lambda1 v1 plus lambda2 v2, so on, till your nth vector, the sum of those is your linear combinations, okay? Your linear combinations form your span. All right. So, another thing to note is that spans are subspaces because, well, because they're attached to arbitrary multiples, lambda1, so on, which can be any value, they satisfy scalar multiplication because essentially you're just multiplying all of your scalars. And it also satisfies scalar addition. Sorry. Also satisfies vector addition, okay? Because, once again, you just add different scalars, which distribute and condense. All right. So, that's out of the way. We know what a span is. We know what a spanning set is. A spanning set is just where the span equals the vector space. So a spanning set is just like, okay, can I make everything possible? All right. First question. Consider the vectors in R3, v1, v2, v3, and b. Prove that b is in the span of v1, v2, and v3, and determine whether or not v1, v2, and v3 make a spanning set of R3. All right. So, first thing to look at here, how are we going to do it? So, prove that b is in the span. Essentially, we need to see that this b, can we make a linear combination of v1, v2, and v3 that construct b, okay? So, our initial thinking of this, if we jump back to high school or wherever we learned our initial algebra, is, okay, we have x, y, and z components. Yeah, if we break it up, we say that, okay, we have a simultaneous equation relating x components, we have a simultaneous equation relating y components, and another for z components. Okay, and that really, it would get us the answer, but it would be a little bit tedious just going through, okay, what is the coefficient of v1, coefficient of v2, and coefficient of v3, okay? But as we learned in Math 1A, which however long ago we may have taken all of that, from 1A we can see that, oh, we can just make a matrix out of this, okay? So if we augment a matrix just like this, okay, where we have v1, v2, and v3, constructing a matrix, then solving for the coefficients of our columns, we can create b, okay? And since we can create b from it, then we've proven that b is in the span, okay? And that is how we're going to do the first part of the question, okay? So, given right here, my bad, I jumped ahead a little bit. Right here, we have augmented a matrix, okay, such that v1, v2, and v3 construct the columns of the matrix, and we're solving for b, okay? And what that's going to do is going to see, okay, is there some multiple of this column plus some multiple of this column plus some multiple of this column that's going to make this column over here, okay? Nice. Now, once we row reduce, okay, which is our most powerful tool in terms of matrices and solving linear systems of equations, we can see that, oh, okay, since our solution, okay, what we're solving for, reduces down to two different row values, with the third row being all zeros, okay, and our matrix on the left side also resolves down to just two rows, we can make it, okay? We can make it because then we can just take multiples of our vectors in here to construct it, which means we've done it. We can make it, okay? It is in the span. It is part of the linear combinations, okay? And that's part A done. Next part of the question is v1, v2, and v3 a spanning set of R3. So, a spanning set. So to determine whether it's a spanning set or not, we need to determine how big is the span, okay? To determine how big the span is, we need to see, okay, are there any existing conditions on x, y, and z, okay? Our three components of our vector, yeah? So to see if there are any conditions, we're going to have an arbitrary vector, which we're going to try and solve v1, v2, and v3 for within its linear combinations, okay? Now, two ways to do this. First way, just described, we are going to go ahead and solve for an arbitrary value. Another way we can do it is to see, okay, if we row reduce, well, if we construct the matrix of v1, v2, and v3, can we arrive at a row-reduced echelon form of the matrix where we have all three of the columns are leading? Okay, what that means is that essentially v1, v2, and v3 become a basis of R3, but we'll cover that later. We're happy with our current method, which will be, we will solve for an arbitrary vector x, y, z, okay? So once we do this and we row reduce, we arrive at a 0 row must equal something. Now, we know for there to be any solutions to this, we know that this little fancy expression over here must be 0, yeah? Another 1a topic, which we are now applying in 1b. Okay, so now that we know that this equals 0, we know that, first of all, this is a plane, okay? Second of all, this does not satisfy everything, okay? There are things that lie outside of this, like, okay, let's say all three of these are 1, okay? X, Y, and Z are 1. We know that 1, 1, 1 is not in, well, does not equal 0, okay? Because you have -3, -1, +1, you get -3, okay? Minus 3 is not 0, so it can't be in this linear combination of v1, v2, and v3. All right, so that question out of the way, linear independence, okay? So linear independence of a set is where, okay, if we think about Legos again, can we make one of our pieces out of the other Legos, okay? Something of that form, because if we can, then we can make 0. We can make 0 out of something that is not 0, okay? So linear independence is where the only solution to the 0 vector is where all of the scalar multiples are also equal to 0, okay? All right, so we have a couple informal definitions, a formal definition. We're happy with our understanding. If we don't understand, once again, head over to the comments section, or you can just redirect yourself to course notes, or even like our MathSoc revision notes, okay? Okay, so we have a couple other ways to determine linear independence. So as I mentioned just a little bit before, we can see that if all of the columns in a matrix, or the augmented matrix, are leading, then it is independent. So if we have something like this, okay, with ones, so like all three of these are leading, okay, then we can say, oh, it's independent. We're happy with that. However, if we instead have something like this, oh, we only have one leading column, this one is not leading, okay? Since it is not leading, it is a dependent set, okay? All right. So, did I miss anything? I think we're pretty happy with this, okay? We can also look at the determinant of matrix, okay? But once again, that is kind of going off of our use of row echelon form, okay? To see if any of the columns are leading. So we will jump into the first question here. First question here is to determine if certain sets are linearly independent or if they are linearly dependent, okay? And give reasons why. We are given the three vectors u, v, and w, which are linearly independent in R3, okay? Just as our basis for constructing our further sets, okay? So, first set, S1, is constructed of one vector, u minus v. Now, because u and v are both linearly independent, stated in the question, we can see that Well, since they're linearly independent, they're not going to be 0, so the only way to make 0 out of linear combinations of just this one vector, u minus v, is to have a multiple of 0, okay, which is just our first bit of information right here, okay? First bit of information, yeah? Since u and v are not equal to each other because they're linearly independent, u minus v is a non-zero vector, so only a multiple of 0 gives us 0, okay? So we have linear independence, okay? We've satisfied the formal definition, okay? Next, the second set, S2, okay? It has our two vectors, u minus v and v minus w. So now we have more than one vector. It gets a little bit more complicated, but what we're going to do here is we're going to attach scalar multiples to both of them and see if we can come up with any conditions that arrive for creating 0, okay? So as we have right here, we have attached two multiples to it, okay, to consider the linear combinations, and we've solved for 0, okay? Now once we do this, we distribute our multiplication, which is one of our vector laws, one of the things we can do. So lambda 1 comes over here and over here. Lambda 2 comes over here and over here. And we see, okay, we have pushed it back into the form of u, v, and w. So since we know that u, v, and w are linearly independent, we know that the only multiple of them, the only linear combination of these three vectors to make 0 are when all of their coefficients are equal to 0. Yeah? If we're happy with that, we can move on, and we arrive at lambda 1 is 0, lambda 2 is 0, and, well, the only thing left is, okay, is lambda 2 minus lambda 1 also 0? Yes, it has to be, because both of them are 0. And so that gives us linear independence. We are very happy. All right. Last one left. We have three vectors in S3, and what we're going to do is we're going to apply a similar kind of approach. Okay, we're going to attach our scalars to them and kind of break it down into the different vectors which we know and understand are linearly independent. All right. Question in the comments section. Where can we find yesterday's revision session? There are a few ways we can find them. Either we can look on YouTube. Okay, MathSoc YouTube, we have our lists of videos. Alternatively, you can look at our website, but as of right now, we're going to chuck a link to that into our comment section. All right. So, question 3. As I said, we're going to attach our scalars to these three vectors, and then we're going to break it down into our linearly independent vectors u, v, and w. Okay? Now, once we do this, we can see we get this, okay? Our scalars distribute as they did the last question, and because u, v, and w are all linearly independent, the only solution to 0 is where all three of these operations of scalars are equal to 0. So this equals 0, this equals 0, and this equals 0, okay? So that's referring to these three scalars we have right here. So if lambda 1 minus lambda 3 is 0, then lambda 1 equals lambda 3. Lambda 2 minus lambda 1 is 0, lambda 2 equals lambda 1. Lambda 3 minus lambda 2 is 0, lambda 3 equals lambda 2. Okay? So because we have all these equations now, they actually fit quite nicely to solve that lambda 1 equals lambda 2 equals lambda 3. Okay? Now, note that this is not necessarily that they are equal to 0, okay? So, with this knowledge in mind, we can go ahead and say, okay, if we just have all of them equal to 1, as just a simple example, we can quite clearly see that the sum of these results into the 0 vector, okay? And therefore, it is linearly dependent, okay? And we're done. Okay, that's the question done. We're happy. We got through it. And next, we're going to move into bases and dimension. Okay, so bases and dimension. Essentially, a base or a basis, okay, is a minimal spanning set for a vector space, okay? A basis is a series of linearly independent vectors which construct a vector space through their linear combinations, okay? So we have our formal definition down. Now for dimensions, okay? Dimensions are rather, when we say R3, it's going to be 3. If we say P6, it's going to be 6, okay? So on, okay? Dimension is just the number of vectors a basis needs to become a spanning set of the vector space. So the number of vectors in a basis gives the dimension, yeah? Very happy. All right. So next, we have a little bit of just quick information for bases. And that is, we have 3 conditions, okay? Rather, we have 3 statements. If any 2 of them are true, the third one is also true, and we have a basis, okay? So if the number of vectors in a set is equal to the dimension of V, is our the number of vectors in a set is equal to the dimension of V is our first condition. Second condition is the set is linearly independent, and the third condition is that the set is a spanning set, okay? So we know that a basis is a spanning set, and a basis has the number of vectors in the dimension of V, okay? So if we have these 2 things, it must be linearly independent, and so on for any 2, okay? Any 2 implies the third. And that's just it for a basis. We're happy with that. We understand it. We're going through, okay? First question is we're going to deal with this fancy kind of field, okay? This fancy kind of field is going to look at a new field GF4, which has 4 elements, defining addition and multiplication, okay? So this is just another way we can work with numbers. We make a new set of numbers and see that, okay, there is closure under addition, there is closure under multiplication. We're happy here, okay? So, well, as well as this, it satisfies the field laws, which we covered somewhere in week 1, week 2, kind of starting vector spaces, yeah? Okay. So, first part of the question, prove that the 3 vectors, b1, b2, and b3, are a basis for f3. Okay, so again, to determine if something is a basis, okay, we need to see that 1, it is a spanning set, okay? 2, the number of vectors is equal to the dimension, okay? And that shows that they are linearly independent. So the easiest way that I see doing this is we're going to make a matrix out of b1, b2, and b3, and we're going to augment it with an arbitrary element of our field, okay? Arbitrary element of F3, okay? So if we do that, we get that, but rather, we could just consider this matrix and row reduce it, okay? And once we row reduce it, we can see that, oh, okay, we get a certain number of linearly independent linearly independent vectors because they all have different leading columns, okay? So we dive into part A, we see the matrix, we row reduce it, and we see, oh, we have 3 leading columns. That's beautiful. We got 3 leading columns. That means we got a linearly independent set. And more so, the dimension of F3 is 3. We got 3 vectors, dimensions 3, we're happy. This must be a basis. We're happy. Okay. So, part B, we're going to just plow right through this, okay? Explain why this set of 4 vectors is a spanning set and not a basis, okay? So, first part of the question, why is it a spanning set, okay? Why is it a spanning set? Well, we can just very quickly see that, okay, B1 and B2 are in it. To span, any span includes a basis, okay, essentially. Any spanning set includes a basis. So, if this is made of B1, B2, and B3, if we can make B1, B2, and B3 out of these given vectors, we have said, okay, we can make a basis which is a spanning set, yeah? So, we're going to do that just very quickly. So we already have B1, B1's down, B3, B3's down. Now we need to make B2. B2 is in both of these two remaining vectors, and we can just say, okay, if we subtract B1, because we already have B1, if we subtract B1 from this one, we have B2, and we have B2. We're happy, we've done it. We're awesome, okay? So, with that out of the way, we can just really quickly say, okay, here we go, we have a spanning set. Now, second part of the question, show that it is not a basis, okay? Now, if we just scroll back up, the third thing we can say about these conditions is that if any one of them is false, then we don't have a basis, okay? A basis satisfies all three of these. Given we only need two of them to show that it's a basis, if any one of them is false, then it's not a basis. So we're going to look very hard at the number of vectors in the set is equal to the dimension, okay? We're going to just keep that in our mind, and we're going to look at how many vectors are in this set. We got 1, we got 2, we got 3, and we got 4, okay? 4 vectors, the dimension is 3, can't be a basis, yeah? And that's that, okay? We're really happy with how we're going, yeah? So, we've shown that it is a spanning set, for 1, and for 2, we've shown that it is not a basis, okay? Now, third part of the question, something that is only needed for 1241, and it's concerning coordinate vectors, okay? So, part 3, part C, is going to ask us to find the coordinate vector v with the basis, coordinate vector of v using the basis b1, b2, and b3, okay? All this is asking us to do is to find the coefficient vector, okay, that we obtain when we augment v with this matrix, okay? So we're just going to solve for v using b1, b2, and b3 and look at the coefficients we get for these 3 vectors, okay? All right. So we're going to do that. We jump down here. And so we solve the augmented matrix using the defined addition and multiplication given to us in the question, okay, which is one of the important pieces of information we can use. And we solve for these coefficients. So over here we see that alpha times something equals beta. Well, we get alpha. We see that then using more multiplication and just really just solving the matrix, we get our coordinate vector, which is going to be beta, 1, and alpha, yeah? So the solution to this goes in our third place, solution to this goes in our second place, solution to this goes in our first place, okay? And there we have it. We have finished the question. We're very happy, we've gotten it right, and we're just plowing through. And that's it. That is for vector spaces, okay? Next up, we have linear transformations, okay? A linear transformation is a mapping, okay? You move something from one vector space and you kind of re-represent it in another vector space, okay? So we take an input as a vector and we get an output as another vector, okay? It doesn't have to be, well, it's a vector space, not necessarily a vector. We can do it with polynomials, we can do it with a ton of things, okay? So a linear transformation, okay, keyword is linear, okay? A linear transformation is one that preserves addition and scalar multiplication. So preserving vector addition, preserving scalar multiplication. Why do we say preserve rather than close? Okay, that's the key difference. Closure is when we have something in a set and we remain in the set, okay? So we stay in this circle by doing our operations, okay? Whereas preserve are simply, okay, when we look at our operations themselves, okay, do they work the same way inside as outside, okay? So from that, we say that preservation of addition is where we can distribute a function like so, okay? And similarly, for scalar multiplication, we can move scalars outside of the function. Okay? The function, the transformation, similar words, essentially. Okay. So, we can combine both of these conditions into one big function, okay? By testing this, where we have multiplication as well as addition, we can prove both of these conditions, that it preserves vector addition and that it preserves scalar multiplication. All right. So, we're happy with this understanding. Vector spaces to vector spaces, so on. We have linear transformations. We're going to dive into our first question, okay? The vector spaces for this question are going to be polynomial vector spaces. So, what we're going to do with this, we can kind of represent P2 as ax plus b, which we can kind of like apply a little bit of isomorphism and look at it as a vector, okay? A and b, because we know that the coefficient x distinguishes a, and so on, okay? Similarly, for P3, that's going to be our ax squared plus bx plus c, or we can also represent it as a, b, and c, okay? Just different ways of looking at it, really. Okay, so now that we have that out of the way, we're going to consider this map, okay? The polynomial map, which will take some input of p of x and use its derivative, multiply it, and so on, okay, to give us something in P3, okay? Polynomials of degree at most 3. And what we need to do is to prove that it is a linear transformation. So we're going to throw this chunky guy at it and see if it holds up, if we can break it down into our right-hand side, okay? So we get on with it. First thing we're going to do is we're going to define, okay? We're going to define some element of P2, okay? So P2 is just going to be some arbitrary element, okay? So, I made a little mistake just before. P2 is degree at most 2, so you're going to have x squared there. P3 is at most 3, so you're going to have x cubed there, okay? A there. So I made a little bit of a blunder. So it would look like ABC for P2 and ABCD for P3. My bad, honestly. What am I doing? Okay, so we jump into it and we're going to define some arbitrary value of P2, which we're going to shove into this transformation and see if the result is linear. Because if we pick it for any value which is part of P2, we can show that yes, it is always preserving addition and scalar multiplication. Okay, so we begin. We define u and we define v, just two different elements of P2. So they're going to have arbitrary values as their scalar coefficients. So we're going to use a, b, c, d, e, and f. And very systematically, we can then define their derivatives, okay? And we can just shove it into the equation. So we're going to take the derivative and multiply it by x squared plus 1, and we're going to multiply the original thing by minus 2x and add those two together, okay? So once we do this with our initial condition, that is, we're going to have the transform of lambda u plus mu v, we result in this bit of a monstrosity. Sorry, all of it, it's 2 lines, my bad. And from there, we're going to see, okay, can we break up the terms? Okay, we're going to find x cubed, we're going to find x squared, and so on, and we're going to try and condense it into a form where we can break it out. Okay, if we can break it up into the form of, okay, we have a derivative multiplied by x squared plus 1, and we have something multiplied by minus 2x, we can see we end up with x squared plus 1 multiplied by this chunk, okay? And we have minus 2x multiplied by another chunk, okay? Now all that is left is to demonstrate that one chunk is the derivative of the other. So we have u and u. So this here is going to be tu, because we have x squared plus 1 multiplied by u dash x, and so on. And similarly for vx, okay? We have all of our terms in the right places, and we can just really condense it down into, fundamentally, what we wanted. We wanted lambda, mu, multiplied by their respective transformations, okay? And we've done it. We have shown that t of lambda u plus mu v equals lambda t of u plus mu t of v, okay? Which is our chunky little condition here, okay? We've proven it, and therefore t is linear, okay? Done, awesome, okay? T is a linear transformation, we're very happy. Next question, okay? Just plowing straight in, okay? Let the linear map t from R2 to R2 reflect a vector in the line y equals the square root of x. Sorry, y equals square root of 3 multiplied by x, my bad. So we're going to show, using this transformation, show that the basis is transformed as such, okay? So to show that the basis is transformed as such, we are going to substitute, okay? We're going to substitute 1, 0, so this, and show that it ends up over here. And then we're going to substitute 0, 1, and show it ends up over here. Something like that, okay? Using the transformation. All right. So there are two ways we can think of this, okay? Two ways we can think of this transformation. The reflection over y equals square root of 3 multiplied by x can be thought of in two ways. We take the line and we can say, okay, if we have a vector right here and we want to reflect it, we get to where it is perpendicular and we flip it over the same distance, okay, to get where it goes to, okay? That's one way. It's a little bit algebra intensive, not the best, okay? One key thing here is that there is no constant, okay? There is no constant on the end of this line equation, which we're reflecting over. So something that remains constant in this expression is our distance from the origin, okay? So if we have some point here which we're reflecting over here, its magnitude from the origin is going to remain the same, yeah? We're going to consider this in a very polar kind of form. So we're going to have a radius and an angle. And because we know that this line essentially has just an angle of 60 degrees here, or pi on 3, okay, for however you want to write it, you can see that, okay, if we look over here, angle 30, we're going to reflect it over the line, so we have angle 30, and we get something over here. And we know that the magnitudes from the origin are going to be the same. And similarly for our x transformation, okay? We're going to apply that. Here's a little bit of a diagram to kind of explain, okay, our distance from x to the line, we make an angle of pi on 3. We've got to reflect that over, so we add another pi on 3. We get to 2 pi on 3. And then for y, we have a pi on 2, which makes an angle of pi on 3 on it. We get pi on 3 back. It's pi on 3 from the start. We can just apply cos and sine using our polar forms. Okay, so from that, we have the magnitude remains the same. And we can see, using polar forms, we have just rotated, okay? A reflection through a line can be demonstrated as a rotation, okay? As long as you have a kind of origin through which you are rotating about, okay? That's the most important thing to gain from this kind of perspective. All right. Awesome. That question out of the way, we're moving on, okay? Another way to represent linear maps is through matrices, okay? So a matrix transforms something from, a matrix transforms a vector of a degree n to a degree of m, okay, through different coefficient multiplications, through linear processes, yeah? So it makes sense for any transformation, any mapping, to be represented by a multiplication, okay, matrix multiplication. Rather, a matrix multiplied by a vector, yeah? All right, so just a little bit extra on linear maps. We know that 0 must be sent to 0, right? Because if we have t of 0, this is going to be the same as t of 0 times v, which is going to be equal to 0 times t of v, which we know is just going to be 0, yep? All right. Happy, okay. So matrix representations, essentially, we can convert any linear transformation into a matrix by considering the transformation of the fundamental basis, okay? So if we have a vector space, okay, like this, just x and y, we can then take these transforms, okay, and plug them in to a matrix, okay? So we would take t of 1, 0, with the next line, sorry, the next column being t of 0, 1, and so on, okay? And that gives us our transformation matrix. So here we have a quick example, which is just gonna push us through into, just like a quick example, push us into the right direction. So we are going to consider this transformation where R3 is turned into R, where we take essentially base 10 of V1, V2, and V3. We can show that it's linear through the same kind of example, t of mu v plus lambda u, and that should be equal to mu t of v plus lambda t of u, okay? So once we show this, well, we can just very quickly see that it should be true because we have linear kind of factors here, okay? Whenever we attach lambda to this, lambda gets attached to this, lambda gets attached to that, so on, okay? And we can also see, well, really, that just attaches addition and multiplication. We're done, okay? Can we represent this as a matrix? Of course we can, okay? We just said we could. So we take tv of 1, well, rather t of 1, 0, 0, and that would become 100, and so on. We get 10, we get 1. So we get a transformation matrix that looks like this, okay? Moving on, next question. Okay, so find the linear map for the reflection of a vector through the line y equals the square root of 3 multiplied by x, okay? So we're going to find the matrix A such that it satisfies this. We'll look at the previous question. Well, we just figured out that taking these two transformations, we get two different vectors. And by our theorem, which we just looked at, matrix representation theorem, we can just go ahead and apply that right here, okay? We've already figured them out, we know that they're true, and we can just construct the matrix, okay? Done it, okay? This goes right there, that goes right there, all done. Next question, okay? Now we're gonna find t of 4, 5, okay? We're gonna transform the vector 4, 5 through t, okay? Now, as we just went over, we have found a matrix, okay? We can just multiply it by the matrix, and that immediately gives us the solution, as given here. Or we can break it up into two components, okay? Where we have 4 times the x unit vector plus 5 times the y unit vector, okay? So on, okay? So, next question, okay. So, we're gonna prove for arbitrary vector spaces that if the transform of certain vectors is linearly independent, then the original vectors must also be linearly independent, okay? From this, we're just going to use the property of the linear transformations to kind of throw these linear combination multiples, okay, outside, right? So to find t0v, then we have some linear combination of our vectors, which will be broken down into our transformations, which then we can see, okay, we have a linearly independent set here, so that means all of our multiples must be 0, therefore all these multiples must be 0. Okay, so then we have all of these are 0, so it must be linearly independent. Okay, nice. Next thing, if the vectors given are linearly independent, then is the set of the transformed vectors linearly independent? We're going to find that it's false, because rather, if we look back at our quick example which we did before, even if this is linearly independent, okay, everything here, just because of the basis, okay, is going to be dependent. Okay, everything has to be dependent because we're dealing with R. Okay, so we already understand that it's not necessarily true. So jumping forward back to where we were, is it true or false? Okay, when we take the transpose, we can see random things can happen. Okay, it is not necessarily true, so we have that it is false. Okay, there is no implication there, so we're happy with our present understanding. Kernel or nullity? Okay, so a linear transform from V to W as vector spaces, the kernel is described as the null space. Okay, the kernel is like, okay, how can we make 0? What results in 0? Yeah, what kind of vectors can we shove into the transformation which give us 0? Okay, we already know that 0 must be part of the kernel, okay, because 0 is always sent to 0, but there are sometimes other things that are sent to 0. Yeah, as we saw just before, we saw something like this. Okay, if x1 and x2 are the same, we get 0. So we have a kind of null space with a, yeah. Okay, so nullity, dimension of the kernel, really quite quick. Okay, so to find the basis of a kernel, any kernel in a matrix A, what we're going to do is we're going to solve the same matrix for the 0 vector. Now once we do this, we can determine the linear combinations which will result in 0. And from linear combinations, we can assign scalars to it to create a basis. Okay, so since we've created a basis now, we can really just say, okay, given any multiple of this vector, any multiple of this vector, we get 0 when we transform. Okay, image and rank. We're going to rush through this a little bit quicker. So image is rather your column space, all the things you can make using the columns in a matrix. Okay, so the image of any transformation is something that ends up in rather the codomain. Okay, what in W can we make from our transformation of V? Okay, so rank, dimension of our image, so rather the dimension of all the things we can make. Note that W is our codomain, rather our image is our range. Okay, just another way to relate it back to 1A kind of concepts. Okay, so when we're finding rank, nullity, and bases, nullity, solve for 0, and then find the number of terms in the basis, or we can just find the number of non-leading columns in the row echelon form. Rank, find the number of leading columns. Yeah? Okay. We have a fancy little theorem here where the rank and nullity should sum to the dimension of V. V being our domain. Okay? So if we have a matrix, I'm just going to try and scribble it right here. If we have 1, 2, 3, 4, okay? If we have 4 of these, the dimension of V is going to be 4. Okay, if we have 4 columns, it's going to be dimension 4. And so the sum of the rank and nullity should be 4. And from that, we can determine the rank and nullity just from one of them and knowing the dimension. Okay? So, quick question. Let D be equal to the matrix, give it. Okay? So, find all vectors B that belong to the image. So rather, we're finding the column space. So to do that, we're going to solve for arbitrary values x, y, and z. So once we do that, b1, b2, b3, we are going to say that, okay, 3 times b2 equals 2 times b3 as our row reduction determines that these two must be equal, or rather their subtraction must be 0, and so we get a plane. Okay, a plane is our vectors b, okay, our image. To find a basis, we're going to find linearly independent vectors which construct it, and then as for our final component, well, rank and nullity, we already know that by finding the basis, we can find the rank, because that'll just be the number of vectors in the basis, and then nullity will be our dimension 3 subtracted from our rank subtracted from our dimension 3. Okay, to find the basis, to find a basis of R3, which contains b, we need to find one more vector, okay, which is going to be linearly independent. Now, the easiest and quickest way we can do this is just by taking the cross product. Okay, by taking the cross product, we can then find something that is perpendicular to both of them. So we have a plane, we find something perpendicular. Another way we could do this is when we row reduce, we go ahead and create another column which will be leading, and then we kind of reverse our row reduction. Or we take a vector from the image, okay? So that gives us what we want, okay? Okay, next is eigenvalues, okay? We're gonna speed through eigenvalues just a little bit because eigenvalues, eigenvectors, really one concept, many applications. So if we have any questions, throw them in the comments. We'll either answer them or answer them. They'll get answered, okay? So moving forward, what is an eigenvalue? Okay, an eigenvalue is simply a multiple of a vector, of some vector, through which a matrix multiplication of the same vector results in the multiple of the vector. Yeah, so all vectors of this form, okay, for some specified matrix gives us certain eigenvalues through which we get eigenvectors, which is our special vector through which this property is made. Okay, so lambda in this case is the eigenvalue of A, and V is the corresponding eigenvector of A. Okay, so one thing to note here is that, okay, what if we attach some scalar multiple to both sides of the equation? Okay, so if we have mu here and mu there, oh, wait a second, we've just multiplied our vector again. Okay, essentially by attaching this mu to the vector, okay, we have A mu V equals lambda mu V. And from this, we can just really easily distinguish that the eigenvector is rather part of a span. Yeah, so some span of eigenvectors, some span of vectors constitute what can be V. Okay, so we call this the eigenspace. Okay, the eigenspace of A is just really the range of vectors. Okay, so the method of determining eigenvalues and eigenvectors is from this equation over here, we move lambda v to the other side, so we have AV minus lambda v equals 0, and then we're going to factor v out. Okay, so we have A minus lambda I. Remember, I is the identity matrix. We can only subtract matrices from each other, not scalars. And we have v on the outside equals 0. If v is a non-zero vector, then we have that A minus lambda I must be 0. Okay, rather the determinant of A minus lambda I must be 0. Okay, and that's what we get right over here. Yeah, just by our just solving to 0 kind of ideas. Yeah. Okay, so when we count eigenvalues, we like to count according to multiplicity, and distinct eigenvalues are something else. Okay, distinct eigenvectors are independent eigenvectors, really things that are not just spans of each other. Yeah, so if I have two different eigenvalues, I should see two different eigenvectors, yeah? Why? Because if I have AT, okay, sorry, AV, just to not confuse things, if I have AV, okay, equals lambda V, this can be represented as a function, okay? Since it's represented as a function, it is a very specific value. It can't be equal to some mu V, okay, where mu and lambda are not the same, okay? Okay, so we're going to jump into diagonalization. Diagonalization is an application of eigenvalues whereby we can compute the powers of a matrix very easily, okay? And we can break up a matrix into a diagonal matrix and an invertible matrix of this form, okay? It's a very powerful concept. We'll see a quick application of it in just a bit, okay? To determine if something is diagonalizable, okay, it must have n linearly independent vectors, yeah? Where n is just like the size of the matrix. Now remember, this is only for square matrices. Otherwise we cannot have a diagonal matrix if it's not square, yeah? Okay, so first example, okay, we're going to find the eigenvalues of C, and for each eigenvalue, find the corresponding eigenvector, okay? Now, a little bit iffy, V rather A, okay? This should be a corresponding eigenvector, because we just explained that eigenvectors occur as an eigenspace, a span, okay? So, to do this, what we're going to do, we're going to subtract lambda I, as we had just previously demonstrated. So C minus lambda I, we get the determinant, which is just going to be our crosses, okay? Kind of sword slashes from top left to bottom right, top right to bottom left when we subtract. So we get 1 minus lambda multiplied by 5 minus lambda minus 2 times 2, okay? And so this will give us a characteristic equation, which when we solve for it, will give us eigenvalues, okay? So this is the characteristic equation expressed as lambda minus 3 all squared, which gives us lambda equals 3 as our solution, okay? Multiplicity 2. Now, remember, we need two distinct eigenvalues, okay? We need two distinct eigenvalues for a diagonalization, yeah? So, when we substitute lambda equals 3, we can see that, okay, we get this kind of vector, row reduce, we get this, solve it, we get, for some parameters t, v2 equals t, v1 equals t, so we get two components of our eigenvector are equal, okay? Rather, we get 1, okay? 1, 1 as our eigenvector. Okay, so remember, second part of the question, is it diagonalizable? Give a reason. We just demonstrated that, it only has one eigenvector, one linearly independent eigenvector. This matrix is 2 by 2. We need two. We need two linearly independent eigenvectors. We only have one, okay? So it cannot be done, okay? It is a defective matrix, okay? All right, powers of matrices, okay? This is where a little bit of the application gets a bit exciting. We have a quick question after this, but after that, okay? Powers, essentially, by expressing A as MD M inverse, okay? So we have k many of these multiples, yeah? Because we know that matrix multiplication is not commutative, so you can't swap them, so you can't say all the time A times B equals B times A. No. Matrices do not work like that. We just learned that in 1A. Okay, so instead, what we can do, we can apply diagonalization, whereby we cancel the corresponding M inverses, yeah? The real power of diagonalization. This makes all of our D's, diagonal matrices, collapse into dk, and because we can just very easily say that, okay, dk, that's just going to be our two diagonal entries, all of our diagonal entries multiplied by themselves each time, which really simplifies our calculation. Okay, so our quick example, A is going to be the matrix 2, 2, 1, 3, rather 2, 1, 2, 3. And what we're going to do is we're going to evaluate A to the 4. Okay, so our quick steps are going to be determine the eigenvalues and eigenvectors. So we take the cross product, which is going to be, well, remember, take away lambda, so 2 minus lambda multiplied by 3 minus lambda minus 2 times 1. Yeah? And when we solve this, we arrive at lambda equals 4 and lambda equals 1. The eigenvectors being 1, 1 and minus 2, 1. And from this, we make a matrix, 1, 1, minus 2, 1. And that would be M. Yeah? Our diagonal matrix is going to be 4, 1, 0, 0, and so on. Once we find the inverse of M, we can then apply this diagonalization idea and solve for a to the 4, which is very handy, very neat. Okay. Moving on. We have a bit of a more difficult question here. Okay? So, this is a bit more conceptual. So, considering a characteristic polynomial p of x of a, so since it's a characteristic polynomial, this should be the polynomial which solves for all the eigenvalues of a. Okay? So x to the n, a n minus 1, so on. Okay? That's p of x. Now, what we're going to do is we're going to replace the value of x with the matrix D. Okay? Remember, D is the diagonal matrix of a, consisting of its distinct eigenvalues. Okay? And so, well, distinct eigenvalues in as diagonal entries and so on. And we're going to replace our constant a0 with a0i. What we're going to do here, essentially, is we are converting this entire polynomial into a series of matrix operations. Okay? Then what we're going to do is we're going to prove that PD equals 0. Okay? Where 0 is the n by n 0 matrix. Now, just a really neat thing we can consider with this is, okay, if D is all of the eigenvalues, yeah? If D is consisting of eigenvalues, and we know that this equation solves for eigenvalues, so it should equal 0 for eigenvalues whenever x is an eigenvalue, because of the diagonal matrix, and all of the matrices in this equation now are diagonal, we can break it up into just our row operations, okay? Our individual simultaneous equations, which are all going to be equal to 0. And they must be 0 because the only thing on these lines are eigenvectors, yeah, which this solves for, okay? And so we have our bit of working, and it breaks up into all of our eigenvalues working together, showing that lambda to the n, rather lambda k to the n plus a n minus 1, so on, their sum in the characteristic polynomial must be 0 because this equation solves to 0 for the eigenvalues. Okay? So, part 2, question 2, we're going to prove that the P of the matrix is going to be 0. Okay? Now, remember, the matrix can be broken down to this, and so when we take P of this matrix, we can break down all of our constants and multiply them by our diagonal matrix. Yeah? Once we do that, we see that, okay, by grouping it like this, we get M inverse multiplied by P of D times M, and because P of D equals 0, we just get 0. Done. Proven. We're happy. Okay. Next up, we're going to use the result in question 2 to show that the matrix 2, 1, 4, minus 1 satisfies a squared equals a plus 6i. So we're going to find, now big hint, uses the result in part 2. We're going to find the characteristic polynomial, we're going to substitute a and let that equal to 0. Yeah? So to find the characteristic polynomial, we subtract lambda I, we solve this, we find that, okay, substituting lambda for a, we get a solution. And so we've proven what is required. Okay? All right. So, final application, solving systems of differential equations. we have, okay, consider a differential equation as a coefficient matrix. Okay, once we do that, we can then apply eigenvalues to solve for the differential equations. Yeah. Now this is just a little bit of a quick explanation of how it works, and then it goes back to the ideas explored in our calculus revision seminar, which was yesterday, and we can direct you to the same video in the comments. Okay, so first things first. So by putting a differential equation of this form, okay, dy over dt equals ay, where y is going to equal our vector of all of our equation, all of our variables. Yeah, you might have y and x here, or you can have y equals, this is y as a vector, remember, y equals y, and then dy on dt, and so on for higher systems of equations. Okay, so moving forward, first order ordinary differential equations, we can solve this system by considering y equals y and x, where y is a vector. So this on dt would equal the coefficient matrix 4 minus 2, 1, 1. Yeah, something like that. And so applying that to this, okay, we've made a coefficient matrix. We can solve for the eigenvalues and then substitute them back in, okay, for the solution. So given these produce, this is a homogeneous equation, homogeneous, we can attach the linear combinations of this to solve it, yeah? So by doing so, we can solve for y and we can solve for x. Next step is, okay, higher order ordinary differential equations. We're going to solve the equation using d squared y over dt squared, okay? So since we have a higher equation, our trick we're going to use is we're going to say, okay, let u equal dy on dt, okay? That way we can say that dy on dt equals d on dt of this vector, which will be y and u, which will be equal to the coefficient matrix y. What is dy on dt? It's u, okay? So since it is u, we're going to put a 1 there, 0 there, because there's no y's in it, there's one u in it. Then for u, differentiating u, we can kind of chuck this stuff over to the other side, comes a positive, so we get 2 lots of y. Sorry, no, that was incorrect. We get 24 lots of y, and we get 2 lots of u, so 2 there. Okay, and that would be our coefficient matrix. Yeah, these kinds of ideas, we can throw them at a large number of equations just to see how we solve it. Okay, so moving forward, higher order differential equations, we do as said, we construct a coefficient matrix and we solve the coefficient matrix to determine the eigenvalues and eigenvectors. Once we have the eigenvalues and eigenvectors, we can jump back to calculus and apply our exponential assumptions, yeah, to solve the differential equations. And so we find our solutions and we take the linear combinations and we're happy, okay? So since we've solved for y2 and y1, which are y and the derivative of y with respect to time, rather t, we can just say, okay, since y is y1 and y2 is kind of like dependent on y1 because it's differential, there we go, we have our answer, we've found y. Okay, awesome. That's going to bring my part to an end, and I'm going to swap out with Aaron, okay?
Nice.
Awesome.
Right, thank you, Otto. Let me just move over. Hello. Alrighty, I'm just going to jump right into it then. Okay, so I'm going to be doing probability and statistics. I'll try to compress it as much as I can in the time that we have left. Yes, okay, great. So here we have a bunch of probability definitions, random properties. So firstly, all of the probabilities need to be between 0 and 1. So you don't have any probabilities that are larger than 1 in this case, and everything is positive. And then if we have our sample space S, right, everything inside the sample space should have a sum of 1, and if you have the empty set, then the probability of that should be 0. Okay, next is if we have the union of two events A and B, then our probability overall would be the sum of these two if they were disjoint. So that means they have no common part in the middle. Okay, next is basically some rules that you should be familiar with already, so I'll just gloss through them quickly. This is the complement rule, which basically just says that if you have if you have the complement of something, so the not, right, then the overall probability for that would be 1 minus, so 1 minus of that. Because the total is 1, so if you're looking for everything that isn't your current event, then you just take the total minus the current event. Okay, next is this, right? So this was the same as the formula up there, but here we have a common part. So if A and B are not disjoint, then this is the inclusion-exclusion principle. Right, so if we were to draw a Venn diagram, then the part that we would be double counting would be the intersection of A and B, and so we need to subtract that if we are looking for the union. Next is pretty obvious. If we have A as a subset of B, then the probability of A should be less than or equal to B. And then next, if S is finite, then the sum, right, this is the sum of all of the events, probability of the events inside our sample space will be equal to 1. Okay, so moving on now, we have conditional probability. Essentially how conditional probability works is that we look at the probability of A given B. So this line in the middle, we can just think of that as our given, right? So first B happens, and then we say that A happens. This formula is equal to P of A and B over P of B. So notice that you can actually express P of A and B as the subject of this, and we get P of A given B multiplied by P of B. So technically, you can actually look at the symmetric case of this. This is equal to P of B given A and P of A multiplied together. So this A and B is very versatile because you are able to express it in terms of A given B and B given A, which we will see very shortly. Okay, so how we deal with conditional probability questions is we really like to draw tree diagrams. Why? Because they're easy to visualize what's happening. One event happens directly after another, right? So that is how we have our A given B, right? And we are able to map out all of the possibilities. So we have a visual representation of everything that we need here. Okay, so just a few important rules, right? The multiplication rule, like I just set up there, you can derive this by rearranging the formula that you want for P of A given B. So yeah. Next is the total probability rule. So all of the ways that I can get event A happening is A given B1, right, multiplied by the probability of B1 happening, added onto A given B2, multiplied by the probability of B2, and so on, right? So this way, we're able to make the probability of A no matter what our initial was, right? So if we had B1 as our initial, then A happens, right? And then if we have B2 as an initial, and so on. So this allows us to sum up everything that ends up with P of A. And then here is Bayes' rule. So Bayes' rule is very useful when you're looking for the opposite. So what I mean by that is if we have A given BK, right, and we want to find BK given A, from the tree diagram, what we can have is all of these values over here. So it's easy for us to find this by using Bayes' rule. Notice that the top is just the same thing as P of B, K, and A. So yeah. Mutual independence. So basically, two events are independent if the probability of A and B is the same as the probability of A multiplied by the probability of B. Okay. Same thing if we have P of A equals to P of A given B, or P of B given A. That is the same here, because no matter what happened initially, the probability of the second event is always going to be the same. It's going to be unaffected by whatever happened initially. Okay, so here's our example for conditional probability. Everybody has seen this question probably with the context of diseases, right? So we have false positives and false negatives. Okay, So let's just get right into it. A diagnostic test is 99% correct when the person has the disease and 95% correct when the person doesn't have the disease. In a population, 2% have the disease. So the reason why we bring this particular example up is that I'm trying to demonstrate that when you have a disease that is very rare, and if you test positive, that does not instantly mean that, oh, the world is ending, right, for me. If the disease is very rare, that means that you have a positive test that may or may not necessarily mean that you actually have the disease. The rarer the disease, the more likely that that test was just a false positive. So we'll see here that there is a very low probability of you actually having the disease despite you testing positive. Okay, so how we tackle this is we immediately draw out our tree diagram, right? So let D be the event that they have the disease, which has a probability of 0.02. So instantly we can see that the probability that they don't have the disease is 0.98. Okay, now if they have the disease, the probability that they test positive would be 0.99. And the probability that they don't test positive would be 0.01. Next is if they have not gotten the disease, then the probability of testing negative, right? So that's when the test is being accurate, as it says, would be 0.95. So just be careful. It's accuracy, right? So it means that if you don't have the disease, you should be testing negative here. So 0.95, and the opposite, the complement, would be 0.05, because we know that overall would do 1 minus. So this gives us all of the branches that we need. What we are looking for is the probability that the person has the disease, so P of the disease, given that they test positive. So that is what we are interested in. Okay, so if we are to find that, we can use the formula that we have from before, right? Or we can use Bayes' theorem. I prefer this form because it's easier to understand and memorize. So we know what the probability of D and T is from our table over here, but we do not know what the probability of P of T equals to. Note that we are able to generate that by looking at all of the cases where they end up with T, so these two. So if we add up the sum of these two branches, then we are able to figure out the probability that they test positive, regardless of whether or not they have the disease or not. So if we were to look at how we sum up the probabilities to find P of T, then we would multiply the two branches together. So this is the first branch at the top, and then this is the second branch at the bottom. Chucking them together in the fraction, we get the answer that is 0.288. So this is approximately 29%, right? That's pretty low. So just because you tested positive for the disease doesn't mean it's doomed for you, right? The rarer the disease, the more likely that this positive test was actually just a scam, right? Because it's actually really hard for you to get the disease in the first place. So you shouldn't be too alarmed if there is a rare disease and you test positive for it. Okay, moving on now. So this one, right, we have urn 1 containing 3 red balls. So let me try to draw that. Yes, I've got colors. So in our first urn, we have 3 red balls and 4 blue balls. Let me just change the color here. So 1, 2, 3, 4. Urn 2 contains the 4 red balls and then 2 blue balls. So 1, 2, 3, 4, and then 2 over there. Yes. Okay, a ball is drawn at random from urn 1 and placed in urn 2. So we pick an urn, right, the first urn here, and we take a ball from there. So let me not use white, that would be counterintuitive. Okay, so let's pick a random ball here. So say we have the red one, and then we place it into the second urn. Notice how once we take the red one out, then the total decreases from the first urn, and the total increases in the second urn. So depending on which color that we drew from the urn, it will change the color, right? The total of the colors in both of the urns. So our probability overall changes. Okay, so what we're looking for is firstly the probability that the ball drawn from the second urn is blue. How we will deal with this is to firstly draw a tree diagram, as usual, right? So if we let R1, if we let R1 be the probability that you draw the red one first, and R2 be the probability that you draw the red one second, and then B is for blue, right? So B1 is blue from the first urn, and B2 is blue from the second urn. We have a probability tree diagram here, and we are able to find what we want. So we want to have the probability that the blue ball is from urn 2. Okay. So if we want to find that, we can find all of the possibilities that give us blue balls from the second urn. So this is the first branch that we want, and this is the second branch that we want. So we multiply this and this, plus this multiplied by that. This gives us both of the branches where the second ball that we have drawn is blue. Okay, so this gives us 18/49. Next, we are looking for the ball drawn, right, when the second urn is red. What is the probability that the ball transferred was blue? So in this situation, for you to be looking at the ball transferred, that means that you have to select this from the first urn. Okay, so what we are essentially looking for is to find the probability that the first ball that we drew was blue, given that the ball that we drew second was red. Now, this probability would be hard to find because this is in the wrong order, right? Because we're looking for the thing that happened first, given the thing that happened second. So how we would approach this is to use Bayes' theorem, or the formula that we used just previously, and we are able to express, right, this in terms of R2 and B1, which we can find easily by doing this branch. So R2 and B1. Okay, so to find that branch, we just multiply everything along that branch, and to find everything that has R2 in it, we need to find all of the branches that have red balls in them. So this one and this one. Great. So adding those together, sticking them in the fraction, again, we get 16/31. Okay, so the third one that we want to find is A, be the event that ball drawn from urn 1 is blue, and B, be the event that the ball drawn from urn 2 is blue. So basically just urn 1 is blue and the second one is also blue. So it's looking for if those two are statistically independent or not. So, okay, what we have here is the check, right? So to check if it's independent or not, we run the test, which is P of A and B, whether or not it is equal to P of A, P of B. Obviously, if you think about it, depending on the color that you've drawn from the first urn, if it was red, you'll have a different number of totals, right, in the right. And if it was blue, you'll also have a different number of totals. So depending on the ball that you picked, you should get a different probability. So like if you just think about it, the probability should be different. But if you wanted to mathematically show that this was true, then what we would do was just to sub it in, right? So this is the probability that the first ball is blue and the second one is blue. And then these are just the probabilities that the first one is blue multiplied by the probability that the second one is blue. Note that this is the same answer that we got from the first part. So the first part showed us that we want to find the probability that the second ball is blue, regardless of whether or not the first one was red or blue, right? So this gives us 18/49. And if we sub it in here, we show that these two sides are not equal to each other, therefore they are not independent. Okay, now I'm just going to go through some more definitions. I'll gloss over this because we should already know this. So with the random variables, right, we have the sample space S, and how this works is we look at the probability of that random variable being equal to a particular value that we are interested in. So if we think about it, it's like a function that maps events in our sample space to a value, a real number, that should be between 0 and 1. Okay, so if we want, say, we have the random variable, we can say that this is an actual number. We define it to give us heads as 1 and tails as 0, right? Then we can find the probability that it flips heads and the probability that it flips tails. So this is how we figure out our probabilities here. Now, it's discrete if all of the numbers of the sample space, so if everything inside the sample space, we can count it. So the image, right, is all of the possible outputs. So if we have this as our event, basically the probabilities, so we can count up all of our events. If it is countable, then it is discrete. Of course, if it's not countable, then it's not discrete. It'll be continuous. Okay, so here, cumulative distribution function is basically just cumulative, right? So if we focus on the word cumulative, then what this ends up happening is we look at all of the values up until this particular value, right? So that's what cumulative means. We add up all of the numbers up until that particular value. So this here, right, is capital F of X. So this is what we note as the cumulative distribution function, CDF. So capital F of X is denoted by all of the probabilities of the random variable X up until that certain number. So if A is less than or equal to B, then since you're adding up all of the numbers up to B, right, for F of B, it should have included F of A in it. So the probability cumulative distribution of A, it should be less than or equal to B. if you're looking for values that are between A and B, then you just look at the values that are from B minus the values from A, because all of the values in A should be already included in the B's. So if you want to take the part in the middle, you just cut off the A's in the beginning. Okay, when you approach negative infinity, the cumulative distribution should start from 0, and when you approach infinity, it should go to 1, because the sum eventually should reach 1, right? So it should basically just be an increasing function. So it's non-decreasing, so it can be constant, but it just can't have a negative gradient because you're adding up numbers continuously, or like it's discrete, right? So you can add up all of the numbers from the very left all the way to the right, so it should be always going up. Okay, probability distribution. So here, right, we have lowercase p, and we denote this as like the probability. So p stands for probability, and that's just the probability of this being equal to this particular value. So note that the sum of all of these probabilities should be equal to 1, like I said before, right? The sum of everything inside the sample space should be equal to 1. Every single probability should be positive. It makes no sense if you have a negative probability, right? So everything adds up to 1, and everything should be positive. This, again, is just for the discrete, right? The cumulative distribution function is just the sum of everything up until that particular x that we're interested in. Okay. Cool. Expected value. So expected value, here is the formula. What we're looking for is basically if we have an infinite number of trials, right? What we'd expect as an average of all of these for each particular random variable is given by the x multiplied by the probability, and then we sum them together. So this is just a weighted sum, right? So if there's something having a bigger probability, then that means that it should have a bigger weighting, right? And if something has a lower probability, then it has a lower weighting. Okay, now if you have a function g of x and you're trying to find the expected value of g of x, then all you need to do is to sub it in, right? So you replace the x with the function and you just do everything as normal. Variance. So variance essentially measures the spread of your data, right? So how it's measured is basically it looks at the mean of the squared deviations from the mean. So this is the deviations from the mean, and we square it to keep it positive, and then we find the average of that. So that tells us how far away all the values are spread around the mean. This is denoted as sigma squared. So sigma is the standard deviation. So you can find the standard deviation by just applying the square root. Okay, this is another formula to find the variance. This is generally more useful. So quickly how we can derive this from the equation above, which is the definition, is if we were to just expand this out, and then this is just equal to e of x squared minus 2e of x mu, and just plus mu squared because these are constants. We'll note that this mu is actually a constant as well. So this, if I did not cram it there, because mu is the same as e of x, then we can just write it like this, and then these two cancel, and we get our desired outcome. Hello, okay. Yes, so we just get that basically. Okay. Scaling and shifting. So just one thing to note, before I say anything about this, variance measures the spread, right? So no matter how we shift our values, it should not affect the variance, because the variance is how far away all of the values are from the mean. So that means that if we were to have a plus b, it does not change the variance. However, for expected value, obviously if you're going to be shifting all of your data, then your data should be moving, and so should the mean, right? So think of expected value as just like some linear thing. So a times of e of x plus that b. Variance, this thing, a, if you want to take it out, be very careful. This is a squared. The reason being that you are squaring the distance from the mean, right? So that gives you your squared term. So when you take out a multiple from inside the variance bracket, you need to square it. Standard deviation is a square root of variance. That's easy. So you just take the absolute value, because square root of a squared is just defined as the absolute value of a. Okay. Bernoulli trials. Essentially, Bernoulli trials is you conduct one thing. Just one thing. It either has success or failure. It has probability p of success and it has probability Q of failure. So obviously you either succeed or you fail, right? So the total should be 1. That means we can find Q is 1 minus P. A Bernoulli process is a sequence of identical Bernoulli trials where the events are mutually independent. So think of some coin flip, right? The coin flip that you just did will not affect the coin flip that you make now, right? So every event that you go in the future is not affected by what you're doing right now. Okay, for the number of successes, this is the formula, right? So this is just basically looking at how many ways we can arrange the ones that are actually successful, and then Q is to look for the ones that are failure, P is the ones that are successful. So if we have K successes and N minus K failures, then this is the powers for the probabilities, and then this combinatorics N choose K just allows us to arrange the order in which these K successes occur. Notice that this is exactly the same distribution as the binomial distribution. The binomial distribution is the distribution of the Bernoulli trials, right? If we have n Bernoulli trials, then that means that we have the binomial distribution. So they're exactly the same. Q is the same as, I can't draw between the slides. No. Q is the exact same as 1 minus P. So yeah, they're exactly the same. Here, the expected value is given by NP and the variance is NPQ. Or you can say that this is NP and 1 minus P. That is also fine. Example now. So this question, it's a simple calculation, but what I wanted to bring up about this is that if you're able to use a shortcut for a question, you should consider doing that, right? So the first time that my friend asked me about this question, I decided to do it the long way, which was I listed out the two cases, so 0 and 1. So if you have a head or a tails, right? You win $3 for each head, so I let that number be 3 for the heads and 0 for tails, because you don't lose anything if you flip tails. Then I look at the probability of those, I list them, and I use the formula, the weighted sum for the expected value. That was long. I realized that actually after doing this question, that you can actually just directly use the formulas that you're given here. How do I apply this? Okay, so if we have the probability of getting ahead as 0.7, then we know that the probability of success should be P equals to 0.7, and the probability of failure should be Q equals to 1 minus P equals to 0.3. Okay, great. So what we are looking for is the expected value of the net amount. So note that you have to pay $5 each time to enter the game, right? So what we are looking for essentially is that E of Y is equal to E of 5 minus. So we have to subtract the 5 and then plus 3x. So we have to pay -5 to enter the game, and then we gain $3 for every head. So if x is the number of heads, then this is essentially what we are looking for. Remember that this is literally the rule that we looked at before, right? So if we wanted to take this and express it, we can just split everything up. The -5 can be taken out, and the 3 can just multiply by E of x. Notice what I've done here. This is n, and this is p. So what I've just done is I've applied the binomial distribution. How I know it's binomial? It's because every single time I flip the coin, right, I have the exact same probability of getting ahead, and they're all independent, right? So if I flip a coin and it lands heads, the next one that I flip may or may not be head. It doesn't have any effect. It's always the same for each time I flip the coin. Also, it is looking for how many heads that I get overall after the 12 flips, right? So this fits our definition of binomial because it is looking for how many heads that we have overall in our 12 flips. Okay, so solving it in, we get 20.2. Next is the variance. So what I want you to understand here is that if we subtract 5, it does not affect the way our spread is arranged around the mean, right? So all of the values are still going to move together with the mean. So if we have 3 of x minus 5, then that's fine. We can just ignore it, and we can just take out the 9, which is 3 squared. And then here is the n, p, q. And that gives us the answer of 22.68. So this method is much easier than having to list out all of the things. So like if we have x0, 3, p, x 0.3, 0.7, and then x squared, 0, 9, and then adding up, subtracting and stuff, right? This becomes a bit tedious. If you just apply the formulas and trust the process, right, the rules have been made so that you can just substitute them in. So we can go ahead, do it, and we get our 2 answers. Nice. Okay, geometric distribution. So how this works is basically you have k trials, right? So all of the trials up until the kth trial have been failures, and you stop immediately when you reach the success on the kth trial. So k minus 1 before should be failures, which means that they have a probability q. Q to the power of k minus 1 because you have q of them in a row, and then p is the one that we have for the kth one. So it's q to the power of k minus 1 multiplied by p. Great. Here is the expected value and the variance. Sign tests. Essentially how this works is we use sign tests as a way to show whether or not some particular event happened by chance, right? Or if it was some like underlying factor. So we test the probability of that event occurring and we compare it to a standard. So say normally we pick 5% or 0.05. If it is less than 0.05% chance of happening, then we say that this thing probably wasn't just randomly done by pure luck, right? There's probably going to be an underlying factor. Here we have algebra being easier than calculus, right? Yeah, because this is our topic, right? So essentially what we do is we look at all of the cases that we have the students doing the same or better at algebra. If it is more extreme, we can have 12, 13, 14, 15, add them together, look at the probability of that, and then make a comparison. See here that 1.76% is less than 5%. So evidently there's some other factor that should be there. It's not just like randomly, oh, today people decided just to randomly say that they are equally as easy, and then somehow 1.76% occurred that everyone is doing better in algebra than calculus. That's not going to happen, right? So half is not going to be the equal probability for algebra and calculus. Cool, probability density function. Essentially how this works is now we are looking at continuous random variables. So we know that the random variable is continuous if the cumulative distribution function, capital F of x, is continuous and vice versa, right? So this is if and only if. So variables can take possible values that cover an interval of the real line. So when we are analyzing this, we are looking for values that are in between two particular numbers. It doesn't make any sense to look for one particular value because it's continuous, which means that we're going to have one thin streak, right? The probability of this value being equal to that just one particular value should be equal to 0 because it's infinitely thin, right? It makes no sense. So what we are doing instead is looking at the probability that it lies between two values, so our interval here. So we can find the PDF, the probability density, by differentiating the cumulative distribution function, and also the limit is that, right, the limit of the diff if you cannot diff it particularly at that point. So we expect that if we were to approach the A minus, so from the left hand side, the value of the probability should be kind of like the same thing as the diff of the cumulative distribution function if you can't actually diff at that particular point. Okay, so here's just a bit more definitions, right? So we already know that the probability of everything should be positive, and the cumulative distribution function sums up everything from the very beginning up until your particular value, right? Because it's continuous, you can take any value from negative infinity to positive infinity. So we start from negative infinity and we go up to a value of x. When you do a question, you generally aren't going to be starting from negative infinity. Sometimes it just tells you maybe between 0 and 1, right? So you can just rewrite this as the integral from 0 to x. So you would pick your own starting point because everything else around it should be defined as 0. Okay, this is just the total probability is equal to 1, and then this is just the probability of the two things being inside that interval is the integral between them. So it's a cumulative distribution function difference from b, f of b, minus f of a. Note here, importantly, that it doesn't matter if this is a strict inequality or a less than or equal to, because the probability of actually being on that value a is infinitely thin, right? It's almost 0. So basically, it doesn't matter if you are strictly larger than or larger than or equal to. Okay, same idea, expected value, right? We are looking at the weighted sum for the discrete. Here we're looking at the integral of the x multiplied by the probability. So f of x is the probability density function. So the integral from negative infinity to positive infinity looks at all of that and sums it up together. expected value, if we have a function, as usual, right, we would replace this function inside here and do the exact same thing that we did for the discrete. Here, right, the exact same rules apply. Variance, remember, if we shift it, the spread does not change, so we do not need to factor in the shifts. We have to remember that there is a square time that we pull out because variance is defined as the distance from the mean squared. Okay, so here's an example. If we want to find the value of alpha, what we can use are the two rules that we have for our probability density function. So firstly, everything is positive. So that's kind of already been factored in, right? We know that alpha has to be positive. Next, we need to know that the sum, if we were to integrate it from negative infinity to positive infinity, should be equal to 1 because that's a total probability. However, note that it's between 0 and 1, so that means that we have to integrate from 0 to 1. And then everything else is 0, right? So that means we can just directly state that the integral from 0 to 1 of this should be equal to 1. And then we can solve for our alpha value. So this is what we get after we integrate it. We substitute our bounds in, and then we see that our values will be equal to 2/3. And then that means that our alpha value is 3/2. Okay. Now, if we want to find the expected value, then to find the expected value, what we need to do is to integrate, right, the x multiplied by the f of x. And then for the variance, it would be the integral of the x squared multiplied by the f of x. So we can go ahead and do that here, right? From 0 to 1, we sub in the bounds, and then this makes it so that we get 3/8 for our expected value and 1/5. This is just simple integration. So if you expand this, you'll note that this is x squared minus x to the power of 4, and this is x minus x to the power of 3. So this is really simple. All you just have to be careful about is that the negative infinity and infinity should be there by definition, but we can alter this to change the integrations from 0 to 1 later on, because everything else is 0, right? So if it's not between 0 and 1, it's 0. So you just only need to consider the values between 0 and 1. Okay, to find variance, we have this useful formula that we looked at before, right? And we have this from 1/5, and this is the expected value squared. So after we sub it in, we get 19/320. Okay, this is called standardization. So essentially how standardization works is we shift down the mean to 0, and then we divide by the standard deviation so that the variance is equal to 1. This way, we can standardize it, right? So everything can be compared to similar distributions. This, you might know from high school, is known as your z-score. So that should bring a few memories. Okay, so normal distribution. You don't actually need to know how this formula works, but you just know that it exists, and it kind of looks like this. I think you should have seen this already. Notice that this tiny thing inside is our z-score. So what we have done by standardizing it is that we have made everything in terms of z, so we can compare different distributions, right, with each other, because everything now has it as the mean being 0 and the standard deviation and variance being 1. So this x minus mu over sigma just allows us to calculate the z-score subbing in. Okay. If we want to find the normal probability, what we do, this is the probability of the cumulative distribution function, so the up until our certain value x. What we do is we replace our x by this, right, and x by this. This is our standardization process. So we can make it so that this becomes a z-score. So if we look for the z-scores that we get on the right-hand side of the inequality, we can look that up in the table, and then we can actually get a numerical value. You can't actually look this up in the table when it's like this, because the table is only defined for 0 and 1. So by standardizing it in this fraction, we can use our table, so like the really big table of values, we can find the particular number that corresponds to this z-score that we want, and we can substitute it in to find the value that we need. Okay, so an example here, average lifetime of 4.2 years. So this is how long they last for. Average lifetime of 4.2 years, so we already instantly know that the mu, which is equal to 4.2 years. Suppose that the lifetime is approximately normally distributed with standard deviation of 1.3 years. So here, our sigma should be equal to 1.3. If he wants to offer a warranty on his phones, but he figures that it's only profitable to do so if he replaces fewer than 2%, So what he wants to do is he makes sure that the probability of the phones failing within the warranty period is less than or equal to 0.02. What warranty length should he offer? So how we tackle this is we have a normal distribution, right? We know that this is the mean and we know that this is the variance, so sigma squared. So how this works is we want the warranty time t to make it so that the probability of the phones failing inside the warranty period is less than 0.02. Notice that it doesn't actually matter if this is less than or equal to 0.02 because the times are like infinitely thin, right? If we wanted to have that particular value. Okay, so chucking it into here, t is the value that we want to solve for, right? So what we do is we standardize it. So minus 4.2 divided by 1.3 minus the mean divided by the standard deviation allows us to get the z-score on the left and this particular value on the right, which will be able to be found in the normal table. We need to find this value so that this probability here is less than 0.02. So going to our table, we see that negative 2.05 corresponds to that value that we're interested in here. So we can now solve for our value of t by substituting that in, and then we get that t is 1.535. So the warranty length should be 1.535 years, so that the probability of the phone failing within that period will be less than 0.02. Okay. Now, normal approximation to binomial distribution. So note that the binomial distribution is discrete, which is why you have rectangular blocks, right? As n approaches infinity, so as you get an increasing number of trials, you get closer and closer to the normal distribution, which is that smooth continuous curve that we see here. So you see how the more trials you take, the smoother it gets, right? So that's why we say that the normal distribution is an approximation for the binomial distribution. Now, I want to introduce you to something called continuity correction. So before I scare you completely with this table, I want to let you know that it's actually not too hard to understand continuity correction. You don't have to memorize this table to get continuity correction. How I personally like to do continuity correction is to think of it like rectangles. So continuity correction is basically what we do when we go from the binomial, which is discrete, to the continuous, which is the normal distribution. What we do is we need to make it so that we look at the value that is outside of that rectangle so that we can actually include the accurate value of the binomial distribution, because the normal is continuous, right? And the binomial is discrete. So if we wanted to approximate it, you can actually get a better approximation if we do continuity correction. So how do we memorize the relationship? Essentially, if we were interested in, say, let me look at this particular example of 5, right? If we wanted to look at all of the probabilities that were less than or equal to 5, then we would include that rectangle over here. Including the rectangle means that if we wanted to have the normal distribution, we should start from here. So this is 5.5. So if we wanted to look for the probability that is less than or equal to 5 for the binomial here, then for the normal, we would actually be looking at the less than or equal to 5.5, because this way we can include that rectangle. Now, if we instead do not want to include that 5, and we say, oh, object arrays are exciting. If we say that we want to have 5 less than 5 strictly, then this will not include this rectangle, right? Because it's not part of it. So the continuity correction should only start from this rectangle. This value is 4.5. So the normal, we would be looking at a value that is less than or equal to 4.5. So that's how I like to remember it. Just look at the rectangle, see whether or not it is included. So that process is summarized in this table, which, as I said before, try your best not to memorize. Okay, so here, 6% of voters support them. So P is 0.06, right? So this party says that 0.06%, 0.06 proportion of people support them. 500 people are asked about their voting intention, so that's N. Suppose that they're true. So what we want to do is we want to find the mean and variance of this binomial distribution. So remember that the mean is given by NP and the variance is given by NPQ. So we can sub those in and easily find the values of 30 and 28.2. Remember that you don't have to derive these values in the exam. You have them with you, you have access to your slides and your notes, so here. Okay. When the survey results are published, it is found that 22 of the 500 people are supported the ANHP. Okay. Use the normal approximation to the binomial to estimate the probability that x is at most 22. So what we are looking for is to find the probability that x is at most means it's less than or equal to 22, right? So that means that we need to find the normal approximation to this. Remember, for binomial, if this is discrete and we're doing the normal, which is continuous, we have to apply continuity correction. If you imagine that rectangle that says the number 22 at it, we will be including this rectangle, so we will be starting from the value of 22.5. Okay, so our normal distribution should start by looking at, the values that are less than or equal to 22.5, which means that we can actually make this standardized, right? Once we standardize it, we have this z-score, and this z-score we can use the table to solve. We don't have this negative value, so we can actually look at it as the reverse. So if we draw the normal distribution and we're looking for this value that is negative, that is symmetrical to the value that is positive on the other side, right? 1.4, 1, 2, 3, 3, so on. So this red area is the same as the blue area. This red area is exactly the same as 1 minus all of the area up until that value of 1.4. So that means that we can do 1 minus p of this. After our manipulation, we can go to our table, find this is 0.9207 for the z-score, for the probability at that z-score, and then we find that our probability is 0.0793, or around 8%. Okay, finally, we have the exponential distribution. So how this works is basically this continuous random variable has this distribution. So lambda e negative lambda t. Expected value is 1 over lambda, variance is 1 over lambda squared. Note that the cumulative distribution function is when we integrate from 0 up until that particular value of x that we're interested in, and it'll actually look like 1 minus e negative lambda t. Okay, let's use this in an actual question. So we won't actually directly apply this, we will just directly use the integral of that to find our values. So here, suppose the life for a car battery of a certain brand has the exponential distribution for which the mean is 60 months. So we already know off the bat that the mean, the mu, or the expected value is 60. Car battery's life runs out when it no longer holds charge. So assume that your car came with a new battery installed at the beginning of the year with 1 year warranty. So what you need to do now is to calculate the probability that your battery runs out within the first 2 years. So note that we are given the values in months. So we need to convert this into our months, 24 months. So the probability that it runs out within that 2 years is P of t less than or equal to 24, because t is just how long it lasts for, right? So if it runs out within 24 months, this is what we're looking for. Now, this is found by looking at the cumulative distribution function. So 0 to 24, well, I keep switching to eraser, 0 to 24, right, of that distribution here. If we integrate this, we get e negative lambda t negative, and we sub in 24 and 0 to get here. And then the probability is 0.330. Note that we got the lambda value by looking at the mean, right? The mean, we know e of x is equal to 1 over lambda. So if we want to find lambda, that's just 1 over 60. Okay, next one, we need to find the probability that it runs out between the 2 and the 4 years. So how that would work is if we want to find it between 2 and 4, then P would be T between 2 and 4, exactly as it says, right? But we need to multiply by 12 because this is in years, but we want to find the months. So what we're actually looking for is a probability that is between 24 and 48 months. So that's what we have right over here. And we do exactly the same integral here, sub in the bounds, and we get 0.221. Okay, the other question parts, I'll just run through these quickly. They're pretty similar. So the question for part 3 is if it runs in within the year warranty, right, you can just look for the probability that t is less than or equal to 12 months, and then you just do exactly the same. And the probability that it lasts longer than this would just be 1 minus of that. And then finally, yeah, there we go. That was a weird finally. Yeah. Finally, we are done with our revision seminar. Okay, that was such a weird way of ending it. Yes, so essentially, if you want to look for more stuff, we have revision sheets on our website for 1231, 1241, 1131, 1141, and 1081. So basically, most of the first year courses. So here is the QR code. Thank you for coming to our revision seminar today. Yeah, it's kind of weird that I ended like this, but yes, thank you. All right.
Good luck with your studies.
If you have any questions, leave them in the comments. Yeah. And
Or
then we'll
join join the Discord.
Yes.
Yeah.
Nice. All right. Cool beans.
All right.
Bye.
Thank you.
Thank you.
Bye.